known to anybody who had some high school math. And here is the same expression expressed in some high-level language. And notice that the high-level expression is almost as good as the real thing. That is, that's why we call it high-level language, because it allows programmers to write in which the flow of control of the program takes all sorts of twists and turns due to if commands, goto commands, function calling commands, and so on. So let's start with an example. Here's a mathematical expression which is well known to anybody who had some high school math. And here is the same expression expressed in some high-level language. And notice that the high-level expression is almost as good as the real thing. That is, that's why we call it high-level language, because it allows programmers to write programs in a style which is very similar to the way we think about these applications, in this case, mathematical expressions. Now, this expression that I have here, b squared minus 4ac, is widely used in some branches of mathematics. So perhaps I can generalize what I have here and use a new function called, I call it disk for a discriminant, because that's the name of this expression in mathematics. And if I have to compute this expression many times in my program, it may make sense to refactor it into a method, give this method or function a name, we call it square root, and use it whenever the need arises. So let's kind of step back and see what we're doing in a sort of greater perspective of programming theory. Well, square root, power, and disk are abstractions. They are not part of the basic language, right? The basic language, whether it's Java or Python or whatever, has a limited syntax and a limited repertoire of commands. But here, I'm allowed to invent so-called new commands as I please, which is wonderful, right? Whenever I need a new function, I just make it up, as I just did with this function that I called disk. And I should ask myself, what about the implementation of these functions? I mean, it's very nice to write disk and put parentheses and assume that someone will deliver this computation, but who will, at the end of the line, provide this, realize this function? Well, the beauty of this practice is that it doesn't really matter. I can invent new abstractions at will and assume that at some point, someone will implement them. This someone will either be myself on another day, or later on today or next week, or someone else will do it for me. If I'm a team leader in some software development company, I can assign one of my team members to do it for me, and so on and so forth. The beauty of this is that the story of implementing these functions is completely separate from the story of using them, and I can begin using them before they even implemented, because I can assume that they will provide some value, and I don't care which value. I can continue to write my program and even debug it using some dummy values and so on. So this is a very elegant practice, and the bottom line is this observation that the basic language can be extended at will. In fact, the basic language is very limited. It has only so many commands, but these extensions are infinite, right? I can make the language, as sophisticated as I please. And this idea of giving the programmer the freedom to add more functionality to the language is perhaps, I'm afraid to say it, but it may be the greatest idea in high-level languages. In fact, in programming in general, the idea that you can extend the language as you please. Another aspect of program control, in addition to functions, is the notion of branching. And using this example of computing the so-called discriminant, because of some mathematical reasons, it makes sense to first check if a is not equal 0, and only then compute this computation. Otherwise, do something else. The logic here is not really important. And if I write this and I give it to a compiler, well, the compiler will generate this pseudo VM code. How the compiler achieves this magic is something that will be dealt with in modules 4 and 5, I think, of the course. So you don't have to worry about it right now. You don't have to understand how this transformation took place. But if you look at the code that was generated, you will realize that we have a whole set of new commands that we haven't seen before. And these commands boil down to branching commands, which are goto, if goto, and label, 3 branching commands, and function commands, which boil down to call, function, and return. So this, in a nutshell, is what we're going to do in this module. We're going to discuss these commands, and we're going to discuss them from 2 different perspectives. One of them will be understanding the abstraction. That is, we have to understand how to do branching and function call and return within the VM language. This is something which can be probably is completely new to most of you, because we know how to do branching and function call and return in a language like Java or Python, but when we go down to the level of the virtual machine, there are other rules of how to do it, so we'll have to learn how to do it. And then we will also have to learn how to actually implement these functions, how to make them actually work and deliver their effect. So 2 very different things, right? Abstraction and implementation. All right, so in the course of learning all these new things, we'll go through some very important take-home lessons. First of all, we will learn, once again, the abstraction and implementation of branching and function commands, and you will understand how they actually work. We will spend a lot of time going through the function call and return dance, if you will, which is a very intricate and fascinating process that happens behind the scene. And in the process of running this dance, the computer also has to sort of allocate memory to the main actors of this dance, which are the functions that calling and returning from each other. So we have to understand how memory is allocated dynamically to executing functions. And we'll continue to talk about stack processing in actually even a much more detailed fashion than we did so far. And obviously we'll have to deal with pointers, and we'll have to complete the VM implementation, which is a very interesting programming assignment. So altogether, we're here for a treat in which you will completely understand how functions call and each other and return safely from these ventures, and you will also have a very rewarding programming assignment. So moving along, let's go to the next unit in which we discuss branching. Here's the big picture of our VM language. In the previous module, we dealt with arithmetic logical commands and with memory segment commands, and now we are beginning to deal with branching commands. So branching is actually a relatively easy concept to comprehend. So far, without branching, our program was completely linear. Every command executed after the previous one. But with branching, we can introduce all sorts of nonlinear path in the flow of control of the program. So the program can progress linearly, and then all of a sudden there's a goto, and we continue the program from some other instruction, and the gotos can go forward, they can go backward. If we go both forward and backward, we can implement loops. So this branching gives me a lot of flexibility. So every one of you who used if statements or while statements has experienced the notion of branching without maybe call it without using the word branching. So at the low level, we have two kinds of branching. We have what we call unconditional branching and conditional branching. So we'll spend a few minutes talking about each one of these flavors of branching, and we'll start with an example. So here's an example of a high-level function that computes the multiplication or the product of two given values, x and y. And it computes it using repetitive addition. So we take x, we put it into some container, which we call a sum, and then we increment sum with x y times. And in order to count y times, we use yet another variable called n, which starts with 1, and you can read the code and understand it. It's rather trivial. I should point out, though, that this implementation of multiplication is very naive and very inefficient. Later on, we'll show a dramatically more efficient multiplication of implementation of multiply. All right, so this is our mult function, and we have this while loop here. And once we compile this high-level code into VM code, the compiler will generate the code that you see on the right-hand side. So you see that what the compiler is doing is it's taking this while loop and rewrites it using goto commands. And in order to achieve this rewriting, the compiler also has to invent and generate some labels and insert the labels in the right places. So one label goes where the while was, and another label goes where the while ends, and the compiler has all this knowledge of how to do it. Now, once again, as I said in the previous unit, you don't have to worry at this point how the compiler actually achieves this magic, because we're going to deal with it extensively later on in the course. So all I want to do is focus on the VM code and see how these goto commands are being used. I don't even have to tell you all this story about the high-level function, but I do it because I want you to understand the context of where these weird VM commands come from. They come from compilation. So let's focus on the goto command. We see an example. We have several examples of goto in this code, so I'm just highlighting one of them. And the syntax is trivial, right? You say goto label, and you expect the computer to jump to execute the command just after label in the code. So if you say goto loop, the next command that will be executed is, let me see, push n will be the next command, because that's the command just after the label loop. All right, moving along. What about conditional branching? Conditional branching is more interesting because it depends on evaluating the truth value of some condition. So if you go back to the high-level code, we see that we had a condition there. The condition was, as long as it is not true that n is greater than y, do this and that, right? So true that n is greater than y, do this. As it is not true that n is greater than y, do this and that, right? So what we have here is the command if go to end loop. That's what the compiler has generated. And notice that whenever we wish to use a conditional go to command, we must first push onto the stack a certain condition or a certain expression that describes a condition, and this expression will have to be evaluated before the conditional go to, because otherwise we will not know whether or not the condition is satisfied. So once again, the rules of the game are that you push the expression, and then when the program runs, this expression will end up being evaluated, and a certain truth value will remain on the stack. And then based on this truth value, the if go to command will know whether or not a jump has to actually materialize. And we see that in this particular example, if you look at the high-level code, the condition is n greater than y. And indeed, when you look at the generated code, we see that we have a push n, push y, gt just before the if go to command. And these three VM commands taken together implement in the VM language the same logic as n greater than y. So once the computer will evaluate push n, push y, gt, it will get the truth value that will determine if a conditional jump should actually materialize. All right, so to recap, we have actually materialize. All right, so to recap, we have three branching commands: goto, if goto, and label, without which we could not generate all these labels. And the implementation of these commands is such that when the VM translator will be asked to implement these commands or to realize them, it will have to generate assembly code that affects the same goto operations in assembly. Now, I assume that you went to the trouble of reviewing assembly language as we requested in module 0 of the course, and if you did that, you should know that the implementation should be extremely simple, because the assembly language also has goto commands whose flavor and style of execution is almost the same as the goto commands of the VM language, and therefore the translation in this case of VM branching commands to branching in assembly is a rather simple exercise, and we expect you to do it on your own. All right, so without further ado, we've dealt with these commands in the previous module, we've dealt with these commands in the current unit, and we are ready to tackle the function commands, which are the real essence of this module. So that's what we'll do starting with the next unit. In this unit, we'll begin to discuss functions, and we'll start with the abstract view of functions, which is to say that if you were a VM programmer, how would you use functions in your code? So, as you well know, high-level functions can be extended using subroutines, functions, procedures, methods, and so on. And you may ask yourself where all these names come from. Well, different languages use different terminology to describe what we will call functions. And we don't have to dwell on this. Everyone understands what is a function. It's kind of a black box artifact. You give it some arguments, push a button, the function does something and returns a value. That's a function. And once again, different languages, for historical reasons, call these functions with different names. All right, so moving to our VM language, we already took care of all the commands that you see here, and now we are finally beginning to talk about how to use and how to implement the notion of functions. All right, so here's an example of where functions come to play. The high-level code may say something like where functions. All right, how to use and how to implement the notion of functions. All right, so here's an example of where functions come to play. The high-level code may say something like square root of a certain value, which is the result of evaluating this algebraic expression. And when the compiler is asked to translate this code, it will produce the following pseudo VM code. Well, first of all, we have to evaluate the expression within the parentheses. So how do we do it? Well, we start with push x, push 17, subtract, and this will give us the result of x minus 17. Then we do push x, push 5, and then we do something that you haven't seen before. We call the function math.multiply. And math.multiply is a function which resides in a class called math, which is part of the operating system that surrounds our virtual machine. So our virtual machine is allowed to interact with this operating system, and because multiply is not part of the VM language, we're lucky to have a multiply method that knows how to compute the product of two numbers. So we use the services of this function. Now, multiply will operate on x and 5. It will replace x and 5 with the result of x times 5. That's the rules of the game. And then I can carry out the addition of the result of the multiplication and the value of x. Then I can call the square root function, which is also part of the math library of the host operating system, and so on and so forth. So we see that the VM language features two types of operators, if you will. First of all, there are the fixed operations, which are the part of the language, add, subtract, and so on. But there are only so many such operations, and so on. But there are only so many such operations. If you want to use other operations, well, you either use functions that someone else has already written, like math.multiply and math.square root, or you can write functions of your own. And once again, you have this wonderful freedom to create and use as many functions as you fancy. In that respect, the VM language is unlimited. You can extend it as you please, which is incredible. And here's another interesting observation. Applying a primitive operator like sub, as we see in this example, has exactly the same look and feel as applying an abstract function like math.multiply or math.square root. In both cases, the rules of the game are as follows, and it's very important to listen and understand what I say. The rules of the game are such that if you want to call a function that expects to get, let's say, 3 arguments, then here's what you do. You push the 3 arguments onto the stack, and you call the function. And then some magic happens, and the result of the function is going to replace these 3 values that you pushed earlier onto the stack. So the values or the arguments that you pushed disappear, and instead what appears on the stack is the return value of this function. If you will follow this logic through the example, you will see that it makes perfect sense, and I recommend that you will now pause the video, take a blank sheet of paper, draw an empty stack on it, and just go through the motions here, go through every command, and see how the stack grows and shrinks, until it comes back with the right value, which is the result of this computation. You can make some assumptions about the values of value of x if you want to make your life easier, but it's not really, that's not important. What's important is to understand, that once again, calling a function and calling a built-in command has exactly the same look and feel. And this is, some very elegant feature of the language, which I hope you appreciate just as much as I do. All right, so how do we define a function in the VM language? Well, here's the function in its source view in some high-level program. So what we've chosen to do here is to revisit the multiplication function that we used in the previous module. So this is our own multiplication. So we're going to shortcut the multiplication method of the operating system, excuse me, and we'll use this one instead because I wanted to see the code. And repeating a comment that I said before, which is completely peripheral to this discussion, this implementation of multiply is very naive and inefficient. The math multiply, however, is a very sophisticated and efficient operation, and we'll discuss it when we develop the operating system in the last module of this course. All right, so the compiler goes to work, translates this high-level mult into pseudo VM code, and what you see on the right-hand side is the final real VM code that will actually be generated. The pseudo VM code I show you just so that we can easily discuss the example, but as you know, we don't have any symbolic variables in VM programs, so the real thing is shown on the right-hand side. Now, one interesting observation here, well, it's not interesting, it's technical, is that the function definition syntax begins with the word function, then comes the name of the function, mult, and then comes an integer, which is either 0, 1, 2, or some other positive or non-negative numbers, and this integer informs the implementation how many local variables this function is going to use. So function mult2 implies here starts a function, the name of this function is mult, and it is going to use 2 local variables. Now, why we have to mention how many local variables we need is something that we'll understand in the next unit, not in this one. All right, so what I do here is repeat the same mult function that you saw before in its VM version, and I also added an integer which is either 0, 1, 2, or some other positive or non-negative numbers, and this integer informs the implementation how many local variables this function is going to use. So function mult2 implies here starts a function, the name of this function is mult, and it is going to use 2 local variables. Now, why we have to mention how many local variables we need is something that we'll understand in the next unit, not in this one. All right, so what I do here is repeat the same mult function that you saw before in its VM version, and I also added line numbers just for reference, so we can have some common language. I also want to introduce some code that shows how we use this mult function. So here's a function called main that at some point includes the command call mult2. And notice the syntax, call mult2. This syntax implies the following. Call, I'm going to call a function. The name of the function I want to call is mult. And the following number informs how many arguments were pushed onto the stack before staging this call. So notice what the VM programmer did here. The VM programmer pushed the constant 8. Then she pushed the constant 5, and then she called mult. So the VM implementation knows that not only we have to invoke the mult function, we have to pass to it the arguments 8 and 5. And we know that we pushed, because the programmer informed me that she pushed two arguments onto the stack. Just for reference, so we can the implementation, how many local variables this function is going to use. So function mult2 implies here starts a function, the name of this function is mult, and it is going to use 2 local variables. Now why we have to mention how many local variables we need is something that we'll understand in the next unit, not in this one. All right, so what I do here is repeat the same mult function that you saw before in its VM version, and I also added line numbers just for reference so we can have some common language. I also want to introduce some code that shows how we use this mult function. So here's a function called main that at some point includes the command call mult2. And notice the syntax, call mult2. This syntax implies the following. Call, I'm going to call a function. The name of the function I want to call is mult. And the following number informs how many arguments were pushed onto the stack before staging this call. So notice what the VM programmer did here. The VM programmer pushed the constant 8. Then she pushed the constant 5, and then she called mult. So the VM implementation knows that not only we have to invoke the mult function, we have to pass to it the arguments 8 and 5. We know that we pushed, because the programmer informed me that she pushed 2 arguments onto the stack. Now, in the function calling terminology, the calling function is sometimes called caller, and the called function is sometimes called callee. So I'm going to use these terms interchangeably throughout the following examples. Now, what I'd like to do next is to go through some runtime simulation that will sort of flesh out how this code actually gets executed. So let us begin with the main view of the world. So I'm going to stop this simulation, this imaginative simulation, in certain points of interest. So what happens after line 3 was executed? So let's look at the code. In lines 1, 2, and 3, I pushed 3, 8, and 5. So the stack is going to contain 3, 8, and 5. And then we commence the command call mult2. Well, this is a rather dramatic turn of events because the main function says I now have to call some other function, and therefore we have to put the main function on hold and go to execute this other function, which we called mult. So here is the view of the mult function, and let's see what happens after line 0. After line 0 gets executed, I get several things. First of all, I get an empty stack. Now when I say I mean I'm now the mult function. The second thing that I get is an argument segment. And notice that this, the second thing that I get is an I mean I'm now the mult. I get several things. First of all, I get an empty stack. Now when I say I mean I'm now the mult function. The second thing that I get is an argument segment. And notice that this argument segment contains the exact 2 values that were pushed by the caller. So I get to see these values, and not only to see them, I know how to call them. They are called argument 0 and argument 1 for me in my world. And then another thing that I get is 2 local variables which are initialized to 0. Now, why do I get 2 local variables? Because look at the function declaration command. It was function mult2. So the VM implementation prepared for me a segment called local with 2 local variables which are initialized to 0. So moving along, what happens after line 7 is executed? Well, let's go through all the commands from 0 to 7. We do a push constant 0. So we push 0 to the stack, and we pop this 0 onto local 0. So that's not terribly interesting because 0, constant 0, the happen variable for me is the thing that I get is 1 for me in my world. And then another thing that I get is 2 local variables which are initialized to 0. Now, why do I get 2 local variables? Because look at the function declaration command. It was function mult2. So the VM implementation prepared for me a segment called local with 2 local variables which are initialized to 0. So moving along, what happens after line 7 is executed? Well, let's go through all the commands from 0 to 7. We do a push constant 0. So we push 0 to the stack, and we pop this 0 onto local 0. So that's not terribly interesting because local 0 was 0 before, so it will remain 0. Fine. Then we push 1 onto the stack, and we pop it onto local 1. So the local segment is going to look like this, right? 0 and 1. Then there's a label loop, great. And the following thing is push local 1 onto the stack. But actually, before that, the argument segment remains the same because we didn't touch it. So let me sort of put it on the screen. And now, going back to command 6, we push local 1 onto the stack, and then we push argument 1 onto the stack. So what we get, local 1 is 1, argument 1 is 5, 6, and right, 0. So and 7, 0, called 2, local, I know how to call them. They are called argument 0 and argument 1 for me in my world. And then another thing that I get is 2 local variables which are initialized to 0. Now, why do I get 2 local variables? Because look at the function declaration command. It was function mult2. So the VM implementation prepared for me a segment called local with 2 local variables which are initialized to 0. So moving along, what happens after line 7 is executed? Well, let's go through all the commands from 0 to 7. Values that were pushed by the caller. So I get to see these values, and not only to see them, I know how to call them. They are called argument 0 and argument 1 for me in my world. And then another thing that I get is 2 local variables which are initialized to 0. Now, why do I get 2 local variables? Because look at the function declaration command. It was function mult2. So the VM implementation prepared for me a segment called local with 2 local variables which are initialized to 0. Segment contains the exact 2 values that were pushed by the caller. So I get to see these values, and not only to see them, I know how to call them. They are called argument 0 and argument 1 for me in my world. And then another thing that I get is 2 local variables which are initialized to 0. Now, why do I get 2 local variables? Because look at the function declaration command. It was function mult2. So the VM implementation prepared for me a segment called local with 2 local variables which are initialized to 0. So moving along, what happens after line 7 is executed? Well, let's go through all the commands from 0 to 7. We do a push constant 0. So we push 0 to the stack, and we pop this 0 onto local 0. So that's not terribly interesting because local 0 was 0 before, so it will remain 0. Fine. Then we push 1 onto the stack, and we pop it onto local 1. So the local with 2 local variables which are initialized to 0 and argument 1 for me in my world. And then another thing that I get is two local variables which are initialized to 0. Now, why do I get two local variables? Because look at the function declaration command. It was function mult2. So the VM implementation prepared for me a segment called local with two local variables which are initialized to 0. So moving along, what happens after line 7 is executed? Well, let's go through all the commands from 0 to 7. We do a push constant 0. So we push 0 to the stack, and we pop this 0 onto local 0. So that's not terribly interesting because local 0 was 0 before, so it will remain 0. Fine. Then we push 1 onto the stack, and we pop it onto local 1. So the local segment is going to look like this, right? 0 and 1. Then there's a label loop, great. And the following thing is push local 1 onto the stack. But actually, before that, the argument segment remains the same because we didn't touch it. So let me sort of put it on the screen. And now, going back to command 6, we push local 1 onto the stack, and then we push argument 1 onto the stack. So what we get, local 1 is 1, argument 1 is 5. We get these two numbers, 1 and 5. And then we go through this whole loop in which we compute the product of the two given numbers, and the two given numbers are the arguments 8 and 5. So we compute the product, we get 40, believe me, I checked this code, and according to the code that was shown in the previous slide, the product is accumulated into local 0. So what happens after line 20? Well, now we are at the end of this computation. So local 0 contains the product, 40. Local 1 contains the value of what we called n in the high-level code. You have to go to the previous slide to see it, and we stop when n exceeds the second argument. The second argument is 5, so local 1 will be 6. That's how we know to stop the code. And the stack now contains 40. Why? Because we did push local 0. Look at instruction number 20. This instruction takes the value of local 0 and puts it onto the stack. Now, we do it because we want to return this value to the caller. And indeed, the next command is return. And the VM implementation knows how to handle return. And in particular, when we say return, the VM implementation takes the topmost value in the stack of the callee, and it does the following trick. It takes this value and it puts it on the stack of the caller instead of the arguments that were pushed previously. So now we go back to the main function. The mult function is gone and forgone, and all its memory resources have been recycled in a process that we haven't seen yet. And now going back to the view of main, I get this, right? Because I pushed 8 and 5, I called mult, I got 40. That's what I expected to get. And then at line 5 of main, I add up these two numbers and I get 43. Very nice indeed. So notice the difference between the abstract view of main and what actually transpired, right? Main pushed two arguments, said multiply, boom, it got the result. It went on to compute add as if nothing happened. But in real, a lot happened behind the scene. So how should we make this abstraction actually work? What we see here is exactly the same code that we had before. And I'd like to now take the view of the implementation. I mean, what do we have to do in order to make this magic work? And let us begin with a call, right? That's where the story began. We call the function, a new momentous event that we are now dealing with. Well, here's what I have to do. For each function call during runtime, the implementation has to do the following things. First of all, it has to somehow pass the parameters, we also call them arguments, from the caller to the callee. Somehow we have to make this a handshake. Then we have to determine the return address within the caller's code, because think about it. We are going now to venture into a new adventure. And when this adventure is going to be completed, we have to return exactly to the next command in the caller's code. So we have to remember this address somehow. We have to remember where to return. So we determine the return address. Then we save the return address somewhere. I mean, what is, when we say remember, it has no meaning, right? We have to save it somewhere in memory. And we also have to save the current state of the caller. And the state consists of, the working stack of the caller, the memory segments. Everything has to be saved so that when we return to the caller's code, we will be able to recreate the private world of main and continue executing as if nothing happened, right? So we have to save the state of the caller, which includes the return address, and only then we can allow ourselves to jump to execute the called function. So all this has somehow has to happen in order to implement and service a call command. Now what about return? Return is also quite involved, right? Because here's what I have to do whenever, as an implementation, whenever I have to deliver a return command. So let's see. I have to return to the caller the value that was computed by the called function, okay? And here you see that there's an underlying assumption, an implicit assumption, which I had to make it explicit, but I'll do it now. It is required that the callee, the called function, always pushes a value before it returns. This is part of the rules of our game. Before you make a return, you must push a value onto the stack, and this is the return value. So the implementation knows that the topmost value on the stack must be the return value. So it knows that it has to return this value, somehow transport this value back to the caller. After doing this, by the way, instead of just saying transporting back to the caller, what it actually has to do, it has to take this return value and put it at the topmost value. It has to push it onto the stack of the caller. That's what it has to do. But before it makes its push, it has to remove the arguments, right, as I explained before. So it's even more involved than that. And then after doing this the return value, because the implementation is a good citizen, it has to recycle the memory segments and the memory resources and the stack and all the the stuff that was used by the call function, because the call function is irrelevant now. Then we have to reinstate or recreate the world of the caller, which is consisting of its saved working stack and memory segments, and only then we can jump to the return address in the caller's code and continue executing it as if nothing happened, right? So this is the view of the implementation. And what we'll do in the next 3 units is we'll actually make this implementation work. interchangeably throughout the following. Function mult2 implies here starts a function, the name of this function is mult, and it is going to use two local variables. Now why we have to mention how many local variables we need is something that we'll understand in the next unit, not in this one. All right, so what I do here is repeat the same mult function that you saw before in its VM version, and I also added line numbers just for reference so we can have some common language. I also want to introduce some code that shows how we use this mult function. So here's a function called main that at some point includes the command call mult2. And notice the syntax, call mult2. This syntax implies the following. Call, I'm going to call a function. The name of the function I want to call is mult. And the following number informs how many arguments were pushed onto the stack before staging this call. So notice what the VM programmer did here. The VM programmer pushed the constant 8. Then she pushed the constant 5, and then she called mult. So the VM implementation knows that not only we have to invoke the mult function, we have to pass to it the arguments 8 and 5. And we know that we pushed, because the programmer informed me that she pushed. But actually before that, the arguments have to save executing it as if nothing happened, right? So this is the view of the implementation. And what we'll do do in the next 3 units is with Unit 4, we start a sequence of 3 units in which we're going to explain how the function calling return protocol, if you will, is implemented. Now, this implementation is non-trivial, and actually it's quite fascinating and somewhat technical, and therefore we decided to devote 3 units to explaining how we have to do it. So we'll begin with a preview in this unit, then we'll do a simulation to see how it actually works behind the scene, and then finally we'll discuss how to actually make it happen. So I'd like to begin by saying a few words about the notion of function execution. As you well know, a computer program typically consists of several functions, or a Java program consists of several methods typically, and if the program is doing something not trivial, it may well consist of dozens of methods which are spread over multiple classes and so on. And yet, at any given point of time, only a very small subset of these methods are actually doing something. For example, foo calls bar, and bar calls square root, and square root may call something else. And all these functions that participate in this example of execution we call all these functions taken together the calling chain. So the calling chain is a completely abstract notion that describes the chain of commands, so to speak. So foo called bar, bar called square root, and that's where we are presently at. Now, think about it. From an implementation standpoint, every one of these functions has some state. It has some private world. And this private world must be maintained as long as this function exists on the calling chain. So what is this state that I refer to? Well, the function state is also an imaginary concept that we use in order to refer to the function's working stack and memory segments. And so taken together, we call these things states. And here is what we have to do with a state. When the function enters its execution, when the function starts running, we have to create a state for this function. We have to give it an empty working stack. We have to give it its local segment and argument segment and so on. And then the function starts doing its things. And as long as the function works, we have to maintain the state. In particular, if this function will call another function, we have to save this state somewhere and know how to return to it when this function ends its execution. Now, when the function returns, well, then at this point, we don't need the state anymore. So we can recycle it in order to be good citizens and in order to make sure that the memory will not be completely consumed. So that's what we have to do with the function's state. So in general, when a caller calls a callee, we will have now 2 states, right? We'll have the state of the caller, we'll have the state of the callee. Once the callee starts running, the state of the caller has to be saved somewhere. And when the callee terminates, we can reinstate the caller's state and continue its execution. So how should we do all this? How should we maintain the states of all the functions up the calling chain? Because remember, the calling chain is not just 2 functions. It can be this function calling this one, calling this one, calling that one, calling that. It may be several functions deep. And we have to repeat what you see on the slide here for every one of these couples of calling and caller and callee. So what should we do? What do you think? What should we do to save all these states? Well, think about it, and then we make one observation. And the observation is that the calling pattern is LIFO, which stands for last in, first out, right? The only function that can return is the function which is currently running, right? Which is the function at the end of the calling chain. And all the other functions are waiting for it to return. So once this one returned, the calling chain shortens, and then this function does something, and then it returns, and the calling chain shortens. And we have to repeat what you see and know how to return to it when. Think about it. From an implementation standpoint, every one of these functions has some state. It has some private world. And this private world must be maintained as long as this function exists on the calling chain. So what is this state that I refer to? Well, the function state is also an imaginary concept that we use in order to refer to the function's working stack and memory segments. And so taken together, we call these things states. And here is what we have to do with a state. When the function enters its execution, when the function starts running, we have to create a state for this function. We have to give it an empty working stack. We have to give it its local segment and argument. Segment and so on, and then the function starts doing its things. And as long as the function works, we have to maintain the state. In particular, if this function will call another function, we have to save this state somewhere and know how to return to it when this function ends its execution. Now, when the function returns, well, then at this point, we don't need the state anymore, so we can recycle it in order to be good citizens and in order to make sure that the memory will not be completely consumed. So that's what we have to do with the function's state. So in general, when a caller calls a callee, we will have now two states, right? We'll have the state of the caller, we'll have the state of the callee. Once the callee starts running, the state of the caller has to be saved somewhere. And when the callee terminates, we can reinstate the caller's state and continue its execution. So how should we do all this? How should we maintain the states of all the functions up the calling chain? Because remember, the calling chain is not just two functions. It can be this function calling this one, calling this one, calling that one, calling that. It may be several functions deep. And we have to repeat what you see on the slide here for every one of these couples of calling and caller and callee. So what should we do? What do you think? What should we do to save all these states? Well, think about it, and then we make one observation. And the observation is that the calling pattern is LIFO, which stands for last in, first out, right? The only function that can return is the function which is currently running, right? Which is the function at the end of the calling chain. And all the other functions are waiting for it to return. So once this one returned, the calling chain shortens it to return. So once this one returned, and all the other functions are waiting function at the end of the calling chain. Currently running is LIFO, which stands for last in, first out, right? Then to save all these states. Well, think about it. And then we make one observation. And the observation is that the calling pattern is LIFO, which stands for last in, first out, right? The only function that can return is the function which is currently running, right? Which is the function at the end of the calling chain. And all the other functions are waiting for it to return. So once this one returned, and running, right? Which is the function at the end of the calling chain. And all the other functions are waiting for it to return. So once this one returned, the calling chain shortens, and then this function does something, and then it returns, and the calling chain, shortens, and so on. So it grows like this. Let me sort of go this way. It grows like this, and then this one returns, and this one returns, and then this one returns. So it grows this way and returns this way, and I do this. Does this remind you of something? Hey, that's a stack, right? I mean, what I describe here looks like the stack that we dealt with all along. So maybe we can use the stack in order to save and retrieve all these function states. What I'd like to do next is to illustrate how this ingenious usage of the stack is going to help me save and reinstate the states of the calling function. So let us start, as usual, with the big picture. And the big picture is that we want to compute the product of 17 and 212. How do we do it? Well, the function is doing something. It sets up for the call, and then it says call mult2, informing the implementation that two arguments were pushed onto the stack, and then boom, something happens, and I'm going to get the product of these two numbers. That's the view of the caller, right? So the net effect of this operation is that the function arguments have been replaced with the function's value, which is exactly what I want. And now to the gory details. And the details are as follows. The function is running, doing something, right? So at some point, it prepares to call another function. So it pushes some values, right? Now, if I'm the implementation which is doing all this, I don't know really that the function is preparing to do anything, but at some point, the function says call foo nargs. Okay, and nargs is the number of arguments that we push onto the stack. Well, once I see this command, I know how to call pushes. At some point, it prepares to call another function. So it pushes some values, right? Now, so it pushes some values, prepares to doing something, right? So at some point, it prepares to call another function. So it pushes some values, right? Now, if I'm the implementation which is doing all this, I don't know really that the function is preparing to do anything, but at some point, the function says call foo nargs. Okay, and nargs is the number of arguments that we push onto the stack. Well, once I see this command, I know how many arguments were pushed onto the stack, and it may be so many arguments, and I call it by the variable narg. And at this point, I know where I can set the arg pointer. Remember the segment pointer arg? Well, it should be right here, right? The arg pointer should refer to the base address of the arguments segments in memory. So from now on, I know that what is above the arg is the working stack of the caller, and what is below the arg are the arguments of the callee. I mean, the arguments that the callee is going to use. Now, what else do we have to do as the VM implementation? Well, recall that previously we said that before we jump to execute the call function, we have to save the state of the caller. Now, what is the state of the caller? It consists of the working stack of the caller and the current segments that it uses. Well, the working stack is saved, right? I mean, look at the stack. It's right there. The working stack of the caller is already on the stack, so it's safe where it is. And now I have to save the segments, and I also have to save the return address. within the caller's code. Now, what is the state of the caller? It consists of the working stack of the caller and the current segments that it uses. Well, the working stack is saved, right? I mean, look at the stack. It's right there. The working stack of the caller is already on the stack, so it's safe where it is. And now I have to save the segments, and I also have to save the return address within the caller's code. Now, taken together, we call these things the function's frame. Okay, so the frame is just a fancy word that we use in order to refer to the return address and the saved memory segments of the caller. Now, put yourself in the shoes of the VM implementation. It can access all these pointers. I mean, all these pointers are available, right? The arg, the LCL, this and that, they are available. So I simply push them onto the stack. And this way I save the base addresses of these segments, and therefore I will be able to return to them later on. Okay, the next thing that I can do is finally, after I took care to do all these very responsible things, I can happily jump to execute foo's code. So that's what I do when I have to field or service a call command. So we came here because there was a jump to execute the foo function. Now think about it. If I jump to execute foo, well, I'm going to hit the command function foo nvars, the beginning of the foo function. Nvars informing how many local variables I expect to have. I now is foo. So the VM implementation looks at this and it has to service this command, and it does it as follows. Well, first of all, it creates a local variable segment for the called function. Now I know exactly how many variables I need. I need nvars variables, and I also have to initialize them to 0. So let's do that. I push nvars zeros onto the stack, and once I do it, I also know that from now on I can refer to these values on the stack as local 0, local 1, and so on. If I want, I can use this syntax to refer to these words in the memory. And once I do it, the call function is ready to take off and start running. So let's assume that the call function is running and doing its things, and in the process it grows its working stack, and it now has a working stack of its own, and its things, and in the process the call function is running and doing its things, and in the process it grows its working stack, and it now has a working stack of its own. And then at some point it is going to return, because all functions return at some point. So at some point the call function is going to prepare to return. Now the preparation from the call function standpoint requires that I push a return value onto the stack. So we do this. Notice we push a return value at the bottom of the stack, and then I say return. And then I say return value at the bottom of the stack. We do this. Notice we push a return value at the bottom of the stack, and then I say return. So now the VM implementation has to service the return command, has to implement this command. How do we do it? Well, here's what we have to do. First of all, we have to take the topmost value from the stack, which we know. Well, here's what we have to do. First of all, how do we do it? Well, the return command has to. Now the VM implementation has to service the return command, has to implement this command. How do we do it? Well, here's what we have to do. First of all, we have to take the topmost value from the stack, which we know is the return value, because these are the rules of the game, and we have to copy it onto argument 0. Why? Because in the net effect of this operation, I want to replace the values of the arguments that the caller pushed with the return value. So we do this, right? We take the return value and we copy it onto the word, which can be referred to using argument 0. The next thing that we do is we want to restore the segment pointers of the callers, right? We want to take the saved LCL, the saved arg, the saved this, the saved that, and turn them into the current LCL, arg, this, and that. By doing this, I'm going to reconnect, so to speak, with these memory segments. Then I want to clear the stack of the call function, which is no longer relevant because the call function is going to die in just a few milliseconds. Then I have to set the stack pointer for the caller, and the stack pointer for the caller should be function is going to die of the call function, which is. Then I want to clear the stack of by doing the save that and turn them into the current LCL, arg, this, and that. By doing this, I'm going to reconnect, so to speak, with these memory segments. Then I want to clear the stack of the call function, which is no longer relevant because the call function is going to die in just a few milliseconds. Then I have to set the stack pointer for the caller, and the stack pointer for the caller should be located just after the return value, right? Just after argument 0. And after I do this, I have to finally jump to the return address in the caller's code and continue executing the caller's code. So after I do all this, here's what happens. Okay, I get the return value, and the stack pointer is positioned just after this return value. And as far as the caller is concerned, he's back in business, and he can continue to do what he did before. Now, before we go on, I'd like to make some peripheral comments. First of all, this may sound very complex, and indeed it is complex. And it shouldn't be surprising that it's complex, because if you think about it, we're actually building here a little brain. A very primitive brain, but a brain nonetheless, because it reminds me of let's say you have a robot which is designed to clean your rugs. Well, that's very nice. So the robot is roaming around cleaning your rugs, and it does it because it runs a program that tells it how to clean the rugs. Now I assume that at some point in the future version of these robots, you'll be able to sort of sit back at your home and watch the robot does its cleaning, and then at some point you will be able to say, "Hey robot, make me a cup of tea." Then the robot will have to stop and start running another function that turns it around and leads it to make a cup of tea, and then it will take the cup of tea and give it back to the master, and then it will say, okay, so this thing is finished, now I have to go back to where? Oh yeah, there was another function of cleaning the rugs, so I'm jumping to this function, my world is restored, I have all my memory segments, and then I can continue cleaning the rugs, okay? So that's what we're implementing here. We're implementing a little brain that can do several things and not necessarily at the same time, but it has this wonderful capacity to stop what it's doing now, start doing something else. And by the way, while he was doing the cup of tea, I could have stopped and say, you know what, before you do the cup of tea, go answer the doorbell. And so it will put this thing on hold. It will go to answer the doorbell, and then will say, okay, where was I? I was making a cup of tea. We'll go back to make a cup of tea, give the cup of tea. Where am I now? Yeah, I'm supposed to go back to do the rugs. So we have to implement here something which is very sophisticated. So there's no wonder that the implementation is not trivial. So that's one thing that I want to say. And the other thing is that we are now in a position to introduce this notion of what we call the global stack. And think about it. Above this stack that we are growing here, there are more states of functions that are up the calling chain, right? Because in this example, we talked only about the caller and the callee, but there are many other pairs of callers and callee up the calling chain, and we have to maintain all these states also. So we get a very large stack, which we call the global stack, that contains everything and contains all the information which we need in order to implement and service the runtime of this program, not only the current function, but the entire program. Now, I can refer to some segment of some subset of this global stack here using the term block, and which I just made up. And notice what the block contains. The block is, we can call it, it's the world of the currently running function. Okay. Now, what does it include? I'm now the currently running function. So my block contains, first of all, my argument segment. You see at the top, we see argument, 0 argument. These are my arguments. Argument segment, running function. So my block contains, first of all, my argument of the notice the stack here of this program, not only the current function, but the entire program. Now, I can refer to some segment of some subset of this global stack here using the term block, and which I just made up. And notice what the block contains. The block is, we can call it, it's the world of the currently running function. Okay. Now, what does it include? I'm now the currently running function. So my block contains, first of all, my argument segment. You see at the top, we see argument, 0 argument. These are my arguments. Then the block contains some gray material that I don't deal with at all, because this is some saved information that belongs to my caller, so none of my business. Then I have my local segments, and then I have my working stack. This is my world. I can operate within this world and do whatever is necessary. So this is the block of the currently running function, and the global stack contains many more such blocks. One block for every function up the calling chain. So that's the global stack. And see argument, 0 argument. These are my arguments. Then the block contains some gray material that I don't deal with at all, because this is some saved information that belongs to my caller. So none of my business. Then I have my callers and callee up the calling in order to notice what the block contains. The block is, we can call it, it's the world of the currently running function. Okay. Now, what does it include? I'm now the currently running function. So my block contains, first of all, my argument segment. You see at the top, we see argument, 0 argument. These are my arguments. Then the block contains some gray material that I don't deal with at all, because this is some saved information that belongs to my caller. So none of my business. Then I have my local segments, and then I have my working stack. This is my world. I can operate within this world and do whatever is necessary. So this is the block of the currently running function, and the global stack contains many more such blocks. One block for every function up the calling chain. So that's the global stack. And before we go on, actually 2 more comments. First of all, notice that the state frame of the caller contains only 4 memory segments, right? Local, argument, this and that. And if you remember from the previous module, we actually have 8 memory segments, right? So we also have constant, temp, pointer, and what did I forget? Constant, temp, pointer, and static. Okay. So I argue that these 4 segments, constant, temp, pointer, and static, don't have to be saved. Okay. And you can think about it yourself. Why we don't have to save them? They don't belong to the world of the function. They belong to some other parts of the machine that we're building. If you don't completely see it, you will see it in the future units. So we save only the segments which are relevant to every function up the calling chain. So that's the global stack. And before we go on, actually 2 more comments. First of all, notice that the state frame of the caller contains only 4 memory segments, right? Local, argument, this and that. And if you remember from the previous module, we actually have 8 memory segments, right? So we also have constant, temp, pointer, and what did I forget? Constant, temp, pointer, and static. Okay. So I argue that these 4 segments, constant, temp, pointer, and static, don't have to be saved. Okay. And you can think about it yourself, why we don't have to save them. They don't belong to the world of the function. They belong to some other parts of the machine that we are building. If you don't completely see it, you will see it in the future units. So we save only the segments which are relevant to the current function. This is one observation I want to make. And the other one, which is kind of more general, is that what we really see here is the stack in all its glory, right? Because the stack is such a remarkable data structure. It not only allows me to run all my algebraic operations and logical operations on the stack, but I use the very same stack not only to execute everything in the program, but also to execute all the behind the scene apparatus that is needed in order to service this program which is currently running, which is really remarkable. Think about it. We have here both sort of the operational memory of the currently running function and program, and we also have everything else, the return address and the memory segments, and everything else is saved on the same stack, and everything works perfectly. So this is really a brilliant apparatus. I mean, this whole idea of using the stack to support the runtime of a computer program. We really see why the stack is so effective. Okay, so that's the global stack, and I want to recap what we did in this unit. Basically, we described how to compute a function in the world of the VM. Very simple. From an abstract standpoint, all you have to do is push as many arguments as the function requires, and then all you have to do is say call foo, and then boom, you're going to get the result, right? And the result is going to be the value of this function evaluated in these arguments, and it's going to replace the arguments that you pushed, and that's it. So from the abstract standpoint, life is very, very simple. From the implementation standpoint, oh boy, we just went through what has to be done, and we haven't even gotten to the details yet, which we'll get to in the next unit. So it's incredible to think about the difference between the abstract view of the world, which is kind of sort of an armchair view of calling a function. Call this function, boom, it happens, I get the result, and all the work that has to be done behind the scene, and the caller doesn't care. I mean, it just does the call and gets the result. And this reminds me of this saying by Arthur C. Clarke, that any sufficiently advanced technology is indistinguishable from magic, because from the abstract standpoint, we had a magic, and you know how much work we had to put to make it happen. So we can also say that any sufficiently advanced magic is also indistinguishable from a lot of work behind the scene. And in the next 2 units, indistinguishable
The footage you are seeing is unedited. The only addition is the...
Guarda,
This debate leads to a final acceptance of Dutilleux, but the women remain suspicious. Dutilleux learns the names of the advance party, Sanjuga and Gio. Nandamar, Nagaya, slowly, cautiously, they explore this alien land on the other side of the river. Following the example of explorers of centuries past, Dutilleux tries to win over the natives with a mirror.
They have never seen their own image, except as a trembling reflection in rivers and pools. Is it an evil eye? A trick of the living dead? Either way, it cannot be investigated without due caution. In the Bronze Age, the Iron Age, and then a knife. Stone Age man, short-circuiting evolution, leaping in the Bronze Age, the Iron Age, to reach the Age of Steel.
From a lot of work behind the scene. And in the next 2 units, we'll continue to talk about this lot of work which still has to be done in order to implement the function call and return protocol. I wish to remind you that because the function call and return implementation is rather hairy, we decided to describe it in 3 separate units. And we went through a preview of what has to be done. And I suppose that by now you understood maybe 50% of what I explained. And in the next unit, in this one, you will understand another half of the remaining 50%. And then in the third one, you will understand everything. So what I'd like to do next is to simulate the function call and return protocol in progress. So let's see how it actually works. And to illustrate it, we'll take an example of a recursive function, factorial. And this is how the function may be written in some high-level language like C or Java. And I'm sure that you've seen this function before, so I'm not going to spend any time on it. And what I do want to show you is what the compiler will do with this function. And basically, the compiler, if applied to this source code, will generate the following VM code, assuming that it's a 2-tier compiler like that of Java, C#, and some other languages. So let's see. We start by compiling the main function, and we want to compute factorial 3. So we push 3, we call factorial, and return. That's what we were asked to do. moving along, I now have to compile the factorial function. So we start with the function declaration, function factorial, and then we evaluate the condition n equals 1. And because we have to do things in the VM way, we push n, we push 1, we ask if they're equal, and if they're equal, we go to a base case, which is a label that the compiler is going to generate and insert into the generated code stream later on. Okay, so if we have to go to, we'll go to a base case. And notice, by the way, that when we push n, push 1, and do eq, the eq is going to consume these two values, right? Base case, that's what we function factorial. And because we start with the function declaration, function factorial, and then we evaluate the condition n equals 1. And because we have to do things in the VM way, we push n, we push 1, we ask if they're equal, and if they're equal, we go to a base case, which is a label that the compiler is going to generate and insert into the generated code stream later on. Okay, so if we have to go to, we'll go to a base case. And notice, by the way, that when we push n, push 1, and do eq, the eq is going to consume these two values, right, and return true or false. And based on this, we're going to make the jump. And now we have to implement the else part of the if. So in the else part, we have to evaluate the expression, actually return the value of the expression n times factorial n minus 1. So we push n, and then we turn to compute factorial n minus 1. Well, how do we do it? We push n, we push 1, we sub, we get n minus 1. We call factorial on this value, and then we call the mult function that we wrote before in order to multiply the result of the factorial in n, and we return. So that's the end of the else. And finally, we need to implement the base case. And so we put this label that we generated before. We label base case. And in the base case, it's very simple. We push 1 and return, because that's what the source code wants to do. And that's the end of the story. We also need to implement the mult function. Because we decided to use mult instead of math multiply. It doesn't really matter. But I decided to omit the code of mult, which in the context of factorial is kind of a service function. You know, it's we use it just to multiply things, and it's not terribly interesting. All right, so that's the pseudocode of factorial, and here's the final code. And we'll now go to explore how it actually works. But actually, before we do this, I'd like to say to say something peripheral, and to point out that once again, you know, I've shown you how the compiler plays its magic, but I didn't say how it actually does it. You know, I showed you the result of the magic, and you may be wondering, how is the compiler, you know, how it knows how to generate these labels and so on and so forth. Don't worry about it. We'll spend a whole module, in fact 2 modules, explaining how the compiler operates. But we can stop for a minute in order to appreciate the beauty of this compiler. Because look at it. I mean, the source code consists of something like, I don't know, 10 commands. Congratulations, we have finished building a modern general-purpose computer system, hardware and software, from the ground up. So now that the task has been completed, we can look back and ask ourselves, how can we possibly make this computer better? How can we make it faster, more useful, more versatile? Well, that's exactly what we're going to do in this module, in Module 7. We'll present several extension and optimization ideas, and I bet that you guys can come up with similar ideas of your own. Each one of these ideas can become the basis of a follow-up, all the API. Once you get all these things in place, then the next design objective happens almost automatically. And this objective, which is probably the most important virtue of any hardware and software project or system, is the ability to modify and extend the system with minimum hassle. This is very relevant because, you see, that's what we want to do in this module. We want to talk about how to optimize and extend the HackJack system. And it's gratifying to know that the system that we are about to modify is well designed. It's gratifying because well-designed systems, you know, lend themselves naturally to such modifications. So we'll be able to do everything in a manageable and predictable way. For example, let's take multiplication and division. Presently, the HackLU can only add and subtract. Therefore, even the trivial operation of multiplying by 2 requires calling an OS function, which is very inefficient. Now, when you think about how to allocate your efforts among various possible optimization projects, you should always think about impact. How can you get the biggest bang for the buck? Now, multiplication and division happen all the times in computer programs, and therefore it clearly pays off to try to optimize them. So let's focus on how we can optimize multiplication, because division is pretty much the same, very similar. Well, in, I think it was Unit 6.2, but I'm not sure. I think in Unit 6.2, we presented a highly efficient bitwise multiplication algorithm, also in Chapter 12 in the book. So we presented this algorithm, and then we went on to implement it using the Jack language. Now, if you want to speed up multiplication, we can take the very same algorithm and implement it not as an operating system function written in Jack, but rather as a hardware chip written or specified in HDL. Once you will have such a chip fully tested in place, you could integrate it into the HEC ALU. But this will also require extending the HEC instruction set, because you have to decide on some binary multiplication opcode. Otherwise, you won't be able to tell the ALU to multiply. Now, if you've extended the binary machine language, then you also have to extend the assembly language. You have to come up with some symbolic mnemonic for representing multiplication. And this, in turn, requires that you also modify the assembler that we built in NanToTetris Part 1. You see, that's what design is all about. You have to decide what you want to do, and then you actually have to do it. So as you see, refactoring multiplication into the hardware, so to speak, entails a very nice sort of cross-section surgery, because it cuts through and affects multiple layers in our computer architecture. And because these layers are highly modular and well specified, every one of them, or every one of these modifications, can be done and unit tested separately. Another thing which is missing in our ALU is bit shifting. Bit shifting can really speed up things like multiplication, division, as well as low-level graphics, graphical operations that manipulate pixels on the screen. And so the trick, once again, if you want to implement bit shifting in hardware, is to design new chips and new instructions that carry out left shift and right shift operations at the hardware level. And once we have these hardware capabilities, we should consider modifying our translators to take advantage of them, to exploit them cleverly. For example, whenever the compiler has to multiply or divide, let me rephrase it accurately. Whenever the compiler has to write code that multiplies or divides a number, which is a power of 2, it can do so by generating code that uses bit shifting instead of standard multiplication. You see, that's an example of what people mean when they talk about optimizing compilers. And by the way, in this module, when we say compiler, we mean both the compiler and the VM translator. So you may have to modify either the compiler or the VM translator or both of them. This is something that you have to figure out yourself in any one of these optimization projects. And by the way, the VM the VM translator can really be optimized in many different ways, because right now it simply translates commands from VM to assembly without trying to generate tight code. And therefore, even the simplest operations like adding one or subtracting one generates several assembly code instructions where in fact you could do it with far less. So that's maybe even an example of yet another optimization project. Now, multiplication, division, bit shifting, VM optimization, all these things are examples of optimizing existing functionality. How about creating new functionality? For example, how about adding mass storage and network access to our computer? That's what we'll discuss in the next unit of a follow-up NanToTetris extension project. And the target code consists of something like 20 commands. Operates, but we can stop for a minute in order to appreciate the beauty of this compiler. Because look at it, the source code consists of something like, 10 commands, and the target code consists of something like 20 commands. And it's remarkable, right? We are compiling a high-level program, and the target code is only twice as long as the source. See, that's the beauty of a two-tier compiler. We don't have to compile all the way to machine language. If we had to compile all the way to machine language, then there would be no way that I could possibly explain to you the target code. But here, we compile to a super elegant intermediate VM language, and therefore, the result is very elegant. And the compiler doesn't have to work hard. So the compilation task is not immense. Moving from Java to bytecode, moving from Jack code to our VM code is not such a big deal. Lots of work, but still very manageable. We'll get to it once again in modules 4 and 5, so stay tuned. We'll get back to this later. So what I described so far was so-called compile time, and now I'd like to turn to explain what happens in runtime. Well, in runtime, we are executing this program, so main starts running, and it informs that it has 0 local variables, which is very nice. And then main pushes, so it starts with an empty stack, it pushes 3, so we get 3 on the stack. And then we have the call factorial 1 command, and notice that the 1 informs that 1 argument was pushed onto the stack. So we can refer to the topmost value now in the stack as argument 0, because we know that this value should serve as an argument, right? 0, because we know that this value should serve as an argument, right? Well, now we have to service the call command. So here's what we do. The first thing that we do is we have to save the frame of main onto the stack. So we save it, okay? Now, the blue dot is something that I added for cosmetic and pedagogic effects. And the blue dot shows the return address in the given code. And notice that this is exactly where we want to return to after factorial finished its operation, right? We want to compute factorial and go to the next command. The next command is return, and therefore the blue dot is correctly positioned in the code. And we save this return address, the blue, on the stack. And then, moving along, we jump to execute factorial. And so we have 0 local variables, so we don't have to add anything to the stack. And then we do the following operations. Push argument 0. So argument 0 is 3. So we push 3, we push 1, we ask if they're equal. They're not equal, because 3 does not equal 1. And therefore, we don't go to base case. The if go to does not work. It's not relevant. And also notice that the IC has consumed these 2 values, argument 0 and constant 1. So the overall effect of these 4 commands on the stack is nil, no effect. So moving along, we now have to look at the commands push argument 0. So we push 3, right? And then push argument 0 again and subtract 1 from it, so we're going to get 3 and 2 on the stack. And then we get to the command call factorial 1. So once again, we inform the implementation that one argument has been pushed onto the stack. We can refer to it as argument 0, and we want to issue a call command. So the implementation is going to save the current, the frame of the current function, the current instance of the factorial function, and the return address is the green, right? Because that's where I want to return to after the address is the green, right? Because that's where I want to return to after the factorial returns. So we save the green also, and we jump to the factorial function. We do a push argument 0, which is 2 now, and then we push a constant 1, and we ask, is it true that 2 equals 1? No, so we ignore the base call. The impact on the net impact on the stack is nil. So we happily move to evaluate these commands or implement these commands. So push argument 0, it is 2, and then we push argument 0 again, we deduct 1, we get 1, and then we call factorial 1, informing that one argument has been pushed onto the stack, so we know that we can call this argument 0, and we have to save the state of factorial. So we save the state, including the return address, which is the violet dot, right? Because after the call, we want to return to the next instruction. So the violet point is properly positioned in the code, and I save it on the stack. So now we go to function factorial 0, and let's see, we push argument 0 onto the stack, which is 1. We push 1 onto the stack, and then we ask, are these two values equal? Is it true that 1 equals 1? The answer is yes, it's true. So we are going to do the jump, and we're going to jump to the base case, right? So we jump to the base case, and here I see that I have to push the constant 1, so we push it, okay? We push the constant 1, and now we have to do a return. Now this is the first time that we have to do a return, or that the return occurs in this simulation. And here's what the implementation does when it encounters this return command. First of all, it gets the return address off the stack. It can pop it. You know, we'll see later how we do it exactly, but we get the return address, which is the violet, and we know exactly where we have to return. You see this, I placed this arrow here, which is going to tell me exactly where I have to return when I finish my little business here. So the next thing I want to do is copy the return value, which I know is the topmost value, onto arg0. So I copy 1 onto arg0, and I get 1. It looks very uninteresting because 1 became 1, but in fact it's not the same 1. It's this new one that was copied, right? And then I have to do, let's see, I have to multiply, right? I have to call mult2. Now, I'm not going to show you what happens when I call multiply, but if I did show you, I had to show all the stack growing and so on. I will omit this, and I will just record the result of multiplying these two values, and the result is 2, right? So 2 and 1 are going to replace with 2. And so I call mult2, 2 and 1 are replaced with the result of mult, which is 2, and I omitted all the details. And then I have to do another return, right? And let's see, I have to do another return. So I get the return address, which is the green, and once again, I know exactly where I have to return to, right? I position this blue arrow next to my intended return value, and then I have to do the copy. I take the topmost value, which is 2, and I copy it onto arg0, and so I get 2. I can get rid of 0, and so I value, which is 2, and I copy it onto arg0, and so I get 2. I can get rid of the frame, which is no more relevant, and I jump to the return address, where I find the command call mult2. So once again, omitting the details, I call mult, I do 2 times 3, I get 6. That's the result, okay? And the next command that I hit in the code is return, right? Well, the return is implemented by first of all consulting the frame, and I see that the return address is blue, so I put my marker on the blue command. Then I copy the 6 on arg0. I get the result 6. I recycle what is got free, and I jump to the blue marker, and I do the return. So at the end of the story, I wanted to compute 3 factorial, so I pushed 3, I called factorial, and boom, I got 6, right? This is the view of the caller. And notice how the caller is completely oblivious of all the drama that took part behind the scene. I mean, it's unbelievable how much work we had to do in order to get this result, 6, right, factorial of 3. And just imagine what would happen if we did something like call factorial 50, right? We'd have to do this 50 times, and the stack would grow, 50 times, and then it will return, because that's the nature of factorial, right? It grows, and then it drills down, and then it drills up. And so you can also imagine what happens if I do call factorial 200. I will probably get a stack overflow, right? I mean, the stack will become too large at some point. And so this is what I wanted to show you in the runtime simulation of the protocol that I just described. And in the next unit, we're going to finally implement it using code. I mean, we'll actually write the code that implements this function call and return implementation, and you will be surprised by the simplicity of this code. and you will be surprised by the simplicity of this code. If you recall, we decided to present the function call and return implementation using 3 different units, and we already went through the preview of what we want to do. We gave sort of an informal runtime experience of the function call and return in action, and in this unit we're going to actually describe how we're going to make it happen, how we're going to implement it. So let's get started. Well, we begin with some VM code, which is quite arbitrary and uninteresting, and yet we're going to use it to illustrate a few things. So we have a function called foo.main and another function called bar.mult. And we assume that these functions emanate, or they come from presumably 2 different classes, right? I mean, VM code, as I explained several times, is something which is typically written by compilers. And therefore, it is safe to assume that if this is compiled Jack code, then the compiler was applied to a directory that included 2 different class files named foo and bar. And foo and bar had at least one function written in them, and we see these functions here, foo.main and bar.mult. And we see that at some point in main's code, it computes this expression that we see in the comments. So it pushes 19, 3, it calls bar.mult, and then bar.mult does some work and pushes a return value and returns. So there's nothing really new here, except that I emphasize the fact that a function may well call another function which historically belonged to a different class. But once everything is compiled into VM code, we lose this notion of classes, and what we get is just a long list of functions that have full names, which is the class name dot function name. All right, so we have a caller and a callee, and that's the typical situation that we discussed, and we have the typical function call and return commands that we are dealing with all the time. And here is the contract by which these 2 parties must play. So let's begin with the caller's view of what is going on here. Before I call another function, I must push as many arguments as the function expects to get. So if I call square root, I know that I have to push 1 argument. If I call mult, I know that I have to push 2 arguments, and so on. So the assumption is that whoever wrote this VM code, whether it's a human being or a compiler, well, he knows what he's doing, so he knows how many arguments to push. Next, I invoke the function by saying call function name nargs, whereas nargs is the number of arguments that I pushed before. After the called function returns, the argument values that I pushed before the call are going to be replaced with the return value that always exists. So I know that when the function returns, something new is going to be at the top of my stack. And this something new is the return value. After the call function returns, all my memory segments magically are exactly the same as they were before the call, except that temp is undefined, and some values of my static segment may have changed because the static segment is visible by all other functions in the application. So it may be that some function that I called, or functions that were called by function, but the function that I called changed some statics, and that's just fine. All right, now what is the contract from the callee's perspective? Let's see. Before I start running, my argument segment has been initialized with the argument values that were passed by the caller. I don't care how, I just know that it's there and it's available to me. My local variable segment has been initialized, and all my locals begin with zeros. Once again, I don't care how, but it's there. My static segment has been set to the static segment of the class to which I belong. And since it's a compiled class, it's the VM file to which I belong. Memory segments, this, that, pointer, and temp are undefined upon entry. My code may well use them, but it's responsible to store some sensible values in them in case I intend to use them. And finally, my working stack is empty. One more thing that is very important in the contract is that before issuing a return command, I hereby agree that I'm going to push a value onto the stack. So issuing a return command, important in the contract is that before issuing a return command, I hereby agree that I'm going to push a value onto the stack. So one more thing that is very important in the contract is that before issuing a return command, I hereby agree that I'm going to push a value onto the stack. So once again, we see something that we said several times. The function must return something before it returns. Now, must push something onto the stack before it returns. Now, think about the situation in which this function began its life as a void method. Suppose it was a void method or a void function at the Jack level. And void functions are not supposed to return a value. And we just said that you must return a value. Well, indeed, this is the case. Even if you're a void function, you must return a value. So you push something. You can push 0, and it's the caller's responsibility to do something with this return value. So if the caller knows that he called a function which is supposed to be void, it can simply toss away the value that was returned by the callee. If you didn't completely understand what I said here about this observation about void functions, then don't worry about it. We'll get to it again when we talk about the compiler. So we described the function call and return protocol from the perspectives of the caller and the callee. And now we turn to describe the perspective of the implementation, which is the third party in this dance here. Now, one way to realize a VM implementation is to write a VM translator. And a VM translator is a program that reads the VM code and translates it into assembly. And in our code, and translates it. Translator is a program that reads the VM code and translates it into assembly. And in our case, it's a heck assembly. And so the VM translator will go through the code and focusing on the function commands. It will, for example, when it reaches the call bar mouth2, it will generate code that realizes this commands. It will, for example, when it reaches the call bar mouth2, it will generate code that realizes this call. When it gets to the function command, it will generate code that realizes the function. Same with the return. This mouth2, it will, for example, when it reaches the call bar mouth2, it will generate code that realizes this call. When it gets to the function command, it will generate code that realizes the function. Same with the return. And what we'll do from now until the end of the unit is that we'll zero in on any one of these things that I just described, and we'll explain what exactly the VM translator does. Now, the big picture is that the VM translator is going to generate code that, reading what is written here, it's going to save the caller's state, the state of the foo.main function. Then it's going to do a few more things to set up for the function call, and finally, it's going to say go to the name of the function. So presumably, the VM translator at some point will generate a label, which is the name of this function. And indeed, if you take a few more lines down the target code, you will see the label bar.mult. So this is how we represent the entry point to a function in assembly, in the translated assembly code. All right, so now we're going to explain exactly what we have to do with this pseudocode here on the right. So let's see, handling a call. We begin with some global stack that includes all sorts of stuff. And it also, obviously, at the tip of the stack, we see the working stack of the current function. So the caller, the current function, is doing all sorts of things. And then all of a sudden, we encounter a call some other function command, and we have to implement this command using assembly. What do we do? Well, since the call command includes the nargs parameter, we know exactly how many arguments have been pushed before, right? Nargs. So we know how many how many of the values on the stack are actually should be treated as arguments. And here's what I do. Okay, the first thing is I push a label onto the stack, and later on, I'm going to use the same label as the label to which I'm going to return after the called function. As the label to which I'm going to later on, I'm going to use the same label as the label to which I'm going to return after the called function terminates. So let's keep this in the back of our mind. I push some label that I generated. We see it on the stack now. Then I push LCL to save the state of the local segment, my local segment. I push my arg, saving the state of my argument segment. I push this, I push that, and then I reposition arg. Now let's think about it. Arg should be repositioned for the called function. Now, where should we reposition arg? Well, obviously, we should reposition it at the beginning of the arg segment, which is right here, right? Now, where is this address? Well, I can calculate it because I know how many things I pushed. I pushed 5 values, so I do st minus 5, and then previously the caller pushed narg's argument, so I know exactly where to position arg for the called function. Then I do LCL equals sp, and that's where I'm going to start to push the local variables of the called function, so that's just fine. And finally, I go to execute the called function. Okay, so I go to execute the called function. They simply simply writing the command in assembly go to and the name of the call function. And now I do something very tricky. I insert into the generated code stream the label that I put pushed before, right? Remember, I generated the label. I gave it some agreed upon name that I have to agree exactly, on all these things at some point. And then I push it. So first I generate it. First I generate it, I push it to the stack, and then later on I output it or I emit it into the generated code stream. So that's exactly what I have to do in order to implement a call command. Now, just to explain what is going on here, this is pseudo assembly code, and you have to take this pseudocode and translate it on a piece of paper into actual heck code, should you decide to implement this thing on the heck platform. All right, moving along, we know how to handle call, so now I want to treat the function command, the command that signifies that a function begins in the code. So let's read the big picture. The big picture is such that whenever we hit a function command, the first thing that the translator does is it takes the function name and generates a label. Okay, and this label will serve as the entry point to the translated assembly code of this function. And then we simply have to write some assembly code that handles the setting up of the function's execution. So let's see how we do that. Here's my stack, and the stack is exactly as it was after the call happened. Because remember, when do we hit the function command? We hit the function command always just after a call command, right? Call, and then I hit the function. So this is the same state as we had at the end of the handling of the call. And now we encounter the function name n bars, which inform how many variables, how many local variables the call function expects to have. All right, so what can I do? I can generate the following assembly code. First of all, I take a function name and generate this label, as I said before, and I write it into the generated code stream, and then I repeat n bars time push 0. Right? I know how many local variables I have to create, and so I execute the call function by simply writing the beginning of the arg segment, and then I push it. So will serve as the entry point to the translated assembly code of this function. And then we simply have to write some assembly code that handles the setting up of the function's execution. So let's see how we do that. Here's my stack, and the stack is exactly as it was after the call happened. Because remember, when do we hit the function command? We hit the function command always just after a call command, right? Call, and then I hit the function. So this is the same state as we had at the end of the handling of the call. And now we encounter the function name n bars, which inform how many variables, how many local variables the call function expects to have. All right, so what can I do? I can generate the following assembly code. First of all, I take a function name and generate this label, as I said before, and I write it into the generated code stream, and then I repeat n bars time push 0. Right? I know how many local variables I have to create, and so I create them, and I simply push as many zeros as necessary, and I basically build the local segment of the called function. And that's it, right? That's all I have to do. And now the function can start doing its thing. So it will do its thing, and at some point it will want to return, right? And this will happen doing its thing. So it will do its thing, and at some point it will want to return, right? And this will happen in our example here. And now I have to handle the return command. So reading the big picture, I have to generate assembly code that moves the return value to the caller, reinstates the caller state, and then does a go to foo's return address, which is the return value in the caller's code. If you look at the middle of the code pane of the generated assembly code, you will see this address right, foo the caller's code. If you look at the middle of the code pane of the generated assembly code, you will see this address there, right, foo $ret.1. So presumably, this is the return value that the VM translator created when it handled the call. If you recall, the call command involved generating a return address, and so I see that I go to exactly this return address. And the question, of course, is how do I know how to do it? And that's That's what you'll see in the next slide. All right, so the called function did some work, right? And it grew its working stack. You know, working stack includes all sorts of stuff that the called function created. And then I have a return command. Now, because everyone is assumed to play by the rules, I know that once I hit a return command, I know for sure that the value at the top of the stack must be a return value, because everyone plays by the rules, right? And play a return command. Now, because everyone created, and then I have a return command. Now, because everyone is assumed to play by the rules, I know that once I hit a return command, I know for sure that the value at the top of the stack must be a return value, because everyone plays by the rules, right? And the function must push a return value before it returns. So the next thing that I have to do is as follows, and this is a little bit involved, but it's really not terribly complicated. First of all, I'm going to create some temporary variable, which I call endFrame, and I'm going to assign the value of LCL to it. So if you look at the stack diagram, you will see that endFrame indeed points at the end of the frame in the host RAM. I mean, the stack is obviously stored in the host RAM somewhere. All right, now the return address must be the contents of the word endFrame -5, right? So endFrame, which is like LCL, if you go -5, you hit exactly the address of the return address, right? The address of the return address. Now I need the asterisk because I want to look inside this word, and this is how I get the return address, and I put it in yet another temporary variable, which I call RET_ADDR, return address, and I sort of put it aside for now. And I have to do all these things in assembly, right? All right, so the next thing that I do is I reposition the return value for the caller. Now, where should the return value should be? The return value should be copied onto arg0, right? And I already have a pointer that is located right on arg0, and this is the pointer arg. So I have to perform the pseudo command arg equals pop, because the pop is going to retrieve the return value off the stack, and then I take this value and I put it in arg. So the result, look at the stack diagram, the result is going to be this. I popped the return value and I copied it onto arg, okay, or to the address that arg refers to. All right, moving along, I know where the stack pointer should be. The stack pointer should be just after arg, because this is the view that the caller expects to get. The caller expects to see a return value and then continue to do his work. So SP becomes arg +1, and now I can begin to recover the various segments that I saved on the stack before. So that should be endFrame -1, the contents of endFrame -1. This should be endFrame -2, arg should be endFrame -3, and LCL should be endFrame -4. So I recovered all my memory segments, and finally I can jump to the return address. Where do I jump? I jump to the address that I retrieved before, that I popped from the stack before, and put it in the variable RET_ADDR. Okay, so this is the logic that I have to now implement in assembly. I mean, you have to implement in assembly when you write the VM translator. Now, another thing that I want you to notice is that once I've set SP below arg, I basically communicate implicitly that everything below SP is, it's just game, right? It's like it's recycled, it's dead, it's irrelevant, because the next push is going to override the memory location where SP shows, and then SP is going to be down, and then the next push will do this. So all the entire block, which is marked as recycled, is no longer relevant. So effectively, that's the situation that now the caller is going to see. The caller is going to see the return value at the top of its working stack, and the stack pointer is going to show to point at the next word in the memory, and that's exactly what we wanted. So we did it. We showed how to implement assembly. I mean, you have to implement an assembly when you write the V. The caller is going to see the return value at the top of its working stack, and the stack pointer is going to show to point at the next word in the memory. And that's exactly what we want. So we did it. We showed how to implement a return that the caller is going to see. The caller is going to see the next word in the memory. And that's exactly what we want. So we did it. We showed how at the top of its working stack. stack, and the stack pointer is going to show to point exactly what we wanted. So we did it. We showed how to implement the caller is going to see. The caller is going to see the return value. At the top of its working stack, and the stack pointer is going to show to point at the next word in the memory, and that's exactly what we wanted. So we did it. We showed how to implement return, and basically we showed how to implement every one of the function calling commands. So to recap, this is our global stack, and we showed how to generate the assembly code that, when executed, will end up building and maintaining this global stack during runtime. And we didn't give you the actual assembly code, but we did give you pseudo assembly. And this code, when you write it in Heck, will actually do everything which is necessary in order to build this complicated world that we described in the last 3 units. And the last comment I want to make, which I think is interesting, is that the code that I showed you is completely language and platform independent. So you don't even have to commit yourself to the Heck platform. You know, the specification that I gave you here is actually a specification on how to implement the VM, our VM language, on any given target platform. We didn't say anything about where this thing is going to be stored in memory, or how I wanted to, which assembly language I wanted to use. Use whatever you want. And this is important because we just gave a universal recipe for implementing our VM language on any hardware platform, any computer out there. But of course, in this course, we'll do it in Heck because simply this is the computer that we are playing with in this particular course. All right, so basically, up until this point, we implemented 3/4 of the language, and with this unit, we are now putting a check mark also on the function commands, and we are done implementing the VM language. In the next unit, we will add a few more technical details on how to do it on the Heck platform, and I'll see you there. All right, we are approaching the end of this module, and in this unit we're going to discuss how to implement the VM translator on the Hack platform. And this is indeed a turning point in this module, because up until now I did not commit myself to the Hack platform, and I described in very general terms how to implement our VM, our virtual machine, on any given computer platform. So now I'm going to make a commitment to a certain target platform, which will be the Hack computer. So I have to give you some information on how to do it. So let us begin with the big picture, which is extremely important. And the picture is that we begin with some Jack program, presumably, and the Jack program is stored as one or more Jack files, which are put in a certain directory, or you may call it folder. And this directory has a name. I call it myprog. And then I'm going to apply the Jack compiler to this entire directory. And the Jack compiler is going to create in this example, two new files, which will be the VM translations of the Jack files. So one will be called by default foo.vm, and the other one is going to be called bar.vm. And every method, constructor, and function in the source code is going to be translated into a VM function in the target code. Now, this process is something that you don't have to worry about, because we're going to discuss it at length later on in the course when we build the compiler. But from now on is certainly our business, because now we are in the world of the VM, and we have to translate this code further. That's what the VM translator is all about. And the VM translator is going to do something dramatic. It's going to take all these different standalone functions and kind of weave them into, well, weave is not a good word, but it will transform them into a single assembly file. So notice how several things got lost in the translation. When we translated from Jack to the VM, we lost the notion of constructors, methods, and functions, because everything became functions. And when we translated from the VM to assembly, we lost the notion of functions, because now we just have a long stream of assembly commands, and we have to use assembly in order to capture the semantics of the source VM code. So this VM translator is actually the program that we're developing in the current project and in the previous one. So that's the big picture, and we're going to write the assembly code on the right-hand side using Hack assembly, because I made this decision that I'm going to implement it on the Hack platform. The assembly code on the right-hand side using Hack assembly, because I made this decision that I'm going to implement it on the Hack platform. And in order to do it, I have to comply to certain conventions. And the first convention is booting. What should I do when I turn on the computer? How will the computer know to execute my my program? So here are the assumptions that I request to make. First of all, there should be a VM programming convention. And the convention is that one file in any VM program must be named main.vm, and one VM function within this file must be named main. Okay, so this is something that first of all, there should be a VM that when I convention comply to certain conventions. And the first convention is booting. What should I do when I turn on the computer? How will the computer know to execute my my program? So here are the assumptions that I request to make. First of all, there should be a VM programming convention. And the convention is that one file in any VM program must be named main.vm, and one VM function within this file must be named main. Okay, so this is something that the compiler has to take care of, because the compiler is going to write this VM code, and it's going to be taken care of, quote unquote, automatically, because we have the same requirement at the Jack level, right? You will see that when we write Jack programs, we also require that at least one class will be named main, and one function in this class will be named main also. So this convention we're going to get it for free, quote unquote. All right, then we need a certain convention in the implementation, in our case in the VM translator. When the VM implementation starts running or is reset, it has to start executing an argumentless. When the VM implementation starts running or is reset, it has to start executing an argumentless operating system function called sys.init. So the VM implementation must begin with this code. It must call sysinit, and sysinit is already programmed at the OS level, which is not our business right now. So sysinit is already programmed to call main.main and enter an infinite loop. So sysinit, once it starts running, will end up causing the programmer's program to start running. As well, the main.main will start running, and then the whole Tetris game, whatever it is, will start executing in front of us. Finally, we need some hardware platform convention to comply to, and that is what is known as the bootstrap code. Okay. we have to somehow call sysinit. So the sysinit will be able to call main. And so we request that the code that you see here will be stored in the computers, in the target computer's instruction memory, beginning in address 0. Because the computer that we built, the hack computer, is programmed to start executing the program, which is stored in the instruction memory, beginning with address 0. That's one of the operational rules of the hack computer. And not only hack, most computers in the world comply to this convention here. So the first thing that the computer will do is it will set SP to 256, and by doing this, it will determine that the stack should begin in this address in the host RAM, and then it will call sysinit. These two things must be done in machine language, in assembly, and that's it. And from this point onward, let the show begin. Everything will roll smoothly because the VM translator will know what to do with every VM command. That's what we did in the last in all the units actually in this module. All right, now in order to generate code that complies to all the explanations that I gave before, we have to propose some standard mapping on the hack platform. I explained in the previous module why we need a standard mapping, and indeed, if you recall, this is just a summary of everything that we did so far. We use the hack RAM, and we use it to store all the pointers that you see here using the scheme here. I'm not going to explain it because we went through it in detail throughout the units. But now I also wanted to see this thing in the overall context of the host RAM. So this is the entire host RAM of the hack computer. It consists of about 32,000 words, and the top 2K words are what we've been discussing all the time. That's the blue stuff on the left. And then we have several other areas on the host RAM, which we call heap, memory mapped I/O, and some unused space. And as far as the VM implementation is concerned, we worry only about the top 2K of the RAM, and everything else is something that is going to be used for other purposes, purposes that are not within the jurisdiction of the VM implementation. So we move on to the last slide in this unit, and that is a documentation of all the special symbols that your VM translator ought to use. So first of all, in the previous module, we decided to use these special symbols, and I'm not going to repeat this information now. And in order to implement everything that's described in this module, we're going to use a few more conventions that you see here. We're going to use 3 more types of special symbols for generating labels. And what I have here is just a screenshot from the book that accompanies this course. You're welcome to read this information on your own. I'm not going to dwell on it because it's very technical and not extremely interesting. So now it's on you to write the VM translator and generate all the code which is necessary in order to implement the VM language. And in the next unit, we'll describe how to actually do it using an implementation language like Java or Python in which you will write your VM translator. So we are approaching the end of this module, and I think that you will agree with me that this module has been both long and challenging. And for me personally, it was also challenging from a physical standpoint because you see, I tape something like 8 such units in a stretch. So I end up standing on my feet for several hours in front of the camera. And normally I'm okay doing it because I feel more energized when I speak standing rather than sitting. But about 2 weeks ago, I broke my leg in a biking accident, and now I wear this brace, and it's kind of aching to stand too many hours. So I will sit for a while. We'll do this unit sitting, and then I guess I'll return to standing. So in this unit, we're going to propose an implementation for your VM translator. And to remind you, the VM translator is a program that starts with some VM code and simply translates it into assembly code. And so it goes through the first command, let's say push constant 17, and it generates code that affects the same semantics in assembly. And then it finds the command go to loop, and it generates code that implements this go to command. It does the same with call. Moving along, it generates code that implements the function command, then the push, then the return, and so on until it hits the end of the input source file. So that's the nature of the VM translator. You shouldn't be surprised because you've already written a basic VM translator. And this basic translator is going to be extended in this project into what we call the final VM translator. So basically, we're going to take the program that you wrote in the previous project and add more functionality to it. All right, now to remind you, the source that we're translating is the VM language, obviously, and the target code that we're generating is written in the HEC assembly code. And in doing all this, we have to comply to using the special symbols that I described in the previous unit. And with that, we are ready to describe our proposed implementation. So here again is a diagram that describes the VM translator in action. And we see that in the previous project, if you recall, you were asked to write a VM translator that translates a single given VM file. Well, in this project, one of the things that we want to extend is the ability to handle more than one VM file. So the VM translator that you write should be able to also handle a directory that contains one or more VM files, as we see in this diagram here. And in any event, it always will generate a single assembly file that contains the sort of sequence of all the functions that we are translating. So the proposed implementation that I outline here is exactly the same as, or contains exactly the same modules that we had in the previous project: parser, code writer, and main. And let us describe every one of these modules in turn. The main module receives as input some string that stands either for a single file or for the name of a directory or folder, if you will, that contains presumably one or more VM files. So it's one of the two. And if you use a language like Java or Python, there are capabilities in these languages to decide if a certain string stands for a single file or a directory. The output of the program should be a file name, a .asm file that contains the assembly code that we're going to generate. The process that the main program is going to carry out is the following. First of all, it will construct a code writer in order to handle the output file, which is still empty at this stage. And then it is going to ask itself if the input is a file or a directory. If the input represents a single file, then it will construct a parser to handle this input file, and then it will go into a loop that marches through every command in the input file, parses it, and hands over the lexical elements to the code writer in order to generate the assembly code. If the input is a directory, it will do what we just described for every VM file in that directory. And that's the end of the story. That's what the main module should do. And as you can see, it is not a very complex extension of what we did in the previous project. All right, moving along, the parser, as usual, handles the processing or the parsing of a single VM file. It reads a VM command, breaks it into its lexical elements, and removes all the white space and comments in the process. And this parser is exactly the same as the one that we developed in the previous project. We don't have to touch it. However, we just want to make sure that the parser also handles the commands that we introduced in this module, which are the branching and function commands. Now, if you followed the requirement that we set in the previous project, your parser should handle these commands as well. But if for some reason you didn't do it, this is the time to include them. All right, so the parser is done. And finally, we have to extend the code writer. So the API of the basic code writer that we developed in the previous project is shown here on the screen. To this API, we have to add some additional functionality. First of all, we'll have a method called setFileName, which we will use to inform the code writer that the processing of a new VM file has just started. And we're going to pass the name of this file as an argument. Then we're going to have another to this API, we have to add some additional functionality. First of all, we'll have a method called setFileName, which we will use to inform the code writer that the processing of a new VM file has just started. And we're going to pass the name of this file as an argument. Then we're going to have another method whose job is to write the booting code that will enable the VM to start working as specified in the standard mapping of the VM on the HEC platform. So write_init is responsible for writing this code. And then there will be 3 methods called write_label, write_goto, and write_if, which produce the assembly code which takes care of the commands label, goto, and if. And finally, 3 methods called write_function, write_call, and write_return, which produce the assembly code that knows how to take care of the respective VM commands. And that's it. Once you do that, you will have a fully functioning VM translator, and you have implemented a virtual machine. Now, the most challenging part in writing this VM translator is writing these 6 methods: write_label, write_goto, write_if. I mean, these 3 methods are relatively simple because generating assembly code that implements if and goto is not a big deal. But then we have to generate the assembly code for function, call, and return. And in doing this, you have to follow all the logic that we explained in the previous units in order to build this incredible cathedral, the stack which moves up and down in order to implement the function, call, and return protocol. So this has been the end of this module. And in the next one, we will discuss the project materials and some recommendations on how to actually build this VM translator. So welcome to Project 8, in which we'll get our hands dirty and complete the construction of a VM translator. Now, I wish to remind you that this is the second project in this course, and yet it is numbered Project 8 because we wanted to create a numbering scheme which continues the numbering of the projects in NAND to Tetris Part 1. We don't assume that you took NAND to Tetris Part 1, but we just wanted to have some global numbering scheme going on. All right, so to remind you, this is where we're at in our grand journey map. We want to build a VM translator, which is capable of translating programs from the VM language into lower level programs written in the HEC assembly language. And we decided to separate this substantial And we decided to separate this substantial development task into two separate projects, Project 7 that you've already completed and Project 8 that we are building now. And each project is responsible for handling a different subset of VM commands. So now the challenge is to implement the branching and the function commands. And that's what Project 8 is all about. So suppose you've already developed your VM translator and now you want to test it. How can you do it? Well, as usual, we're going to supply a whole set of VM programs and request that you use them to test your translator. So you have to take every one of these programs, translate them using your translator, and produce in the process another sort of lower level program written in the HEC assembly code. And then we can take this code and simply execute it on the target platform after we translate it further into binary code. Now, alternatively, instead of using the HEC platform, we can use the CPU emulator, which is significantly more user-friendly because you don't have to translate it into machine code. You can run the assembly as is, and for other reasons. So that's what we recommend to do. And now you look at the results of the program if the program performs what assembly code. And then we can take this code and simply execute it on the target. To take every one of these programs, translate them using your translator, and produce in the process another sort of lower level program written in the HEC assembly code. And then we can take this code and simply execute it on the target platform after we translate it further into binary code. Now, alternatively, instead of using the HEC platform, we can use the CPU emulator, which is significantly more user-friendly because you don't have to translate it into machine code. You can run the assembly as is, and for other reasons. So that's what we recommend to do. And now you look at the results of the program. If the program performs what the VM code sought to perform originally, then we're happy and we say that the translator has passed the test. And in fact, we do much more than that because we provide elaborate test scripts and compare files, and so the testing procedure will be very well managed. You don't have to worry about it too much yourself. You just have to concentrate on writing a well-behaving VM translator. All right, so here is the set of programs that we supply in Project 8. If you will look at the Project 8 folder on your computer, assuming that you've downloaded the NAND to Tetris software suite, you will see two directories named program flow and function calls. And each one of these directories contains several subdirectories. If you look, for example, at basic loop, you will see that basic loop contains 4 different files, the star of whom is the VM program. I mean, that's the beef, right? That's what we want to translate. But we have, as usual, several other programs and files. And here's what we recommend to do. Very similar to what we did in Project 7. We recommend that you first invoke the VM emulator and use the supplied XXX VME test script to load the VM program into the simulator and play with it a little bit. Even though it's a testing program, it makes sense to understand what the program seeks to do. This will just give you some background information about the test context. Once you understand what the program wants to do, you don't have to get into the details. You just VME test script programs and files. And here's what we recommend to do. Very similar to what we did in Project 7. We recommend that you first invoke the VM emulator and use the supplied XXX VME test script to load the VM program into the simulator and play with it a little bit. Even though it's a testing program, it makes sense to understand what the program seeks to do. This will just give you some background information about the test context. Once you understand what the program wants to do, you don't have to get into the details. You just have to get a feeling of the program's intended operation. Then you should use your translator to translate it into an assembly file whose name by default will be xxx.asm. When I say by default, your VM translator has to make this default happen. And finally, you can now load and run the XXX test script in the CPU emulator, and this script will run the generated code, the code that was generated by your translator. It will execute it, and it will compare the output of this code to our supplied compare file. If the comparison will be positive, you will get a nice message, and you can proceed to run the next test. If not, then presumably you have to fix a few things in your VM translator. All right, so that's the basic routine, and with that, let's take a look at the basic loop.vm. It will compare the output of this code to our supplied compare file. If the comparison will be positive, you will get a nice message, and you can proceed to run the next test. If not, then presumably you have to fix a few things in your VM translator. All right, so that's the basic routine, and with that, let's take a look at the basic loop.vm test file. As you see from the documentation, this is a VM program that wants to sum up the numbers 1 plus 2 all the way up to argument 0 and push the result onto the stack. So presumably VME found information to an assembly file whose name by default will be xxx.asm. When I say by default, your VM translator will compare the output of this code from test file the next test. If not, then presumably you have to fix a few things in your VM translator. All right, so that's the basic routine, and with that, let's take a look at the basic loop.vm test file. As you see from the documentation, this is a VM program that wants to sum up the numbers 1 plus 2 all the way up to argument 0 and push the result onto the stack. So presumably someone is going to initialize argument 0 for us. In particular, there is a test script called basicloop.tst, and indeed, as you see, this test script, which is stored in a separate file, is going to initialize the virtual memory segments as well as argument 0, and then it will execute the machine code that will be generated after you translate the code that you're now going to see. Well, this was quite a twisted sentence. All right, so here's the code. You can read it if you want. It's not terribly important because here's what this code is doing. It is a simple loop that implements some sort of a while, if you will. As long as, we begin by setting a counter variable to argument 0. As long as counter is greater than 1, we add counter to sum, and we then decrement counter, go to check again if it's still greater than 0, and so on and so forth. So nothing sophisticated here. What is more important is that this program, or this file, is designed to test the ability of your VM translator to handle label and if goto commands. This is the most important purpose of this test file, and everything else is irrelevant details. So this is a basic loop, and you can ask yourself where this VM code is coming from. Well, I don't remember if we wrote it ourselves or if we wrote a Jack program and compiled it into this VM code. It's not terribly important. What's important, once again, is that this program is designed to perform a relatively simple test of your ability to handle branching commands. So with that, let's move forward and take a look at the Fibonacci series test files. So here's the VM program. It seeks to compute the first argument 0 elements of the Fibonacci series. So if argument 0 will be, for example, 5, it will compute the first Fibonacci element, the second, the third, all the way up to 5. And it will put these values in the RAM starting at the address which is stored in argument 1. So once again, someone has to initialize argument 0 and argument 1 for us. And in particular, there is a test script called Fibonacci series.tst, and it will do these initializations, and then it will run the code that will be produced by your VM translator from what we're now going to see. So we begin by approaching or manipulating some esoteric virtual segments like pointer and that, and we don't really expect you to understand exactly what we're doing here, because how to use pointer and that judiciously is something that we're going to explore later on in the course. So for now, suffice it to say that what we do in this code is the following logic. We compute the Fibonacci array, so ARR at I equals ARR at I minus 1 plus ARR at I minus 2, which is the classical Fibonacci transformation or function. And once again, what's important for our purpose is that this VM program is designed to test the ability of your VM translator to handle label, goto, if goto, as well as many other commands in the VM language. So that's the story about Fibonacci series. I wish to emphasize once again that you don't have to spend too much time understanding the details of this program because the details of the semantics are not terribly important for our translation task, which is what we're focusing on right now. All right, so this completes the testing of the branching commands, and now we move on to test your ability to handle functions, which is far more challenging in terms of the time that you spent on implementing your VM translator, I assume. All right, so simple function is a bunch of 4 familiar files, and here is a simple function.vm. It performs and test script. So here's the function, or it's value that goes back to the caller. And command next is as you read contract to a program, let's say in Java, and then you provide translator. It should be that's the contract that we require in the same directory. So VM, and as you see, so here's my Fibonacci element directory. And as you see, there's something new here. And what is new is that this is the first time, I believe, that we see more than one VM program or VM file in the same directory. So as you know, when we have more than one VM file in the directory, we have to translate the entire directory. That's the contract that we requested that you implement in your VM translator. So once you see the prompt on your computer, it should vary from one computer to another. You write VM translator if you wrote this program, let's say in Java, and then you provide the name of the directory. The result should be a single file called Fibonacci element.asm. It is the responsibility of your VM translator to produce this file, and now we can take this file and test it further. All right, so with that, let us explore what we have in these 2 VM files, beginning with main. So main contains a single function called Fibonacci, and this function computes the nth element of the Fibonacci series, and it does it recursively, as opposed to what we did before, which was using an array. And by the way, this program has nothing to do with the program that we used before, which was called, I think, Fibonacci series. Of course, there's a mathematical relationship between them, but it's a completely different program and a rather different algorithm. So how do we compute the nth element of the Fibonacci series? Well, here's how we do it. We do it using recursion. So if you stop the tape and look carefully at the code, you will see that we are calling the Fibonacci function is calling the Fibonacci function twice, and thus what we do here is we implement the logic that you see here in this callout, and classical recursive computation of Fibonacci element. There's nothing terribly important here as far as our limited context of testing your VM translator, but if you want, you can try to understand this code deeper. Not terribly important. What's important is that it serves to test our translator. All right, so this is the same program abbreviated, and we have to invoke it somehow. We have to call this function. So we do it using the sysvm file, another test file in this directory. And this file, we decided that it will have a single function only called sysinit. Now, you may remember that according to our convention, sysinit should call the function main.main, and then the application starts running. However, in Project 8, we decided to use this function differently. And in particular, we use sysinit in order to invoke all sorts of test functions as we please. Now, this whole setting is very useful because by convention, when you start running the VM implementation, it should call sysinit. And then sysinit will call the test function. So things are well laid out. So here's what we do. We decide to test the Fibonacci element function using, say, the number 4. So we wanted to compute the fourth element of the Fibonacci series. So we push 4, call the function, and then we enter an infinite loop. Why? Because we decided that this will be the standard way to implement sysinit. When we complete building the whole computer and the operating system and everything, sysinit will be the first function that starts running when the computer is booted up, and it is the origin of everything, so to speak. So sysinit calls main.main, and then Tetris starts, or your search engine starts, or whatever it is that you decided to write using our platform. All right, so notice that this test here is designed to test the handling of the function, return, and call commands, and as well as many other commands that can be found in these two VM files. And we also test that your VM implementation, the VM translator that you wrote, initializes and handles the memory segments correctly. Up until now, we provided test scripts that have set the virtual segments manually. Now it is your responsibility to handle it using your VM translator. And finally, we also test that the bootstrap code of your VM implementation initializes the stack pointer, and calls sysinit. If you're not sure what I'm talking about, you have to look back at the units that define what the translator is supposed to do, and you will see all the details there. All right, so this is going to be quite an elaborate test, and I hope that your VM translator will pass it without too much trouble. And yet, when we first released all these tests to the public domain and people started using it, our colleague, Mark Armbrust, who contributed tons of good stuff to this course, Mark pointed out that the testing gap between the simple function and the Fibonacci element is too big, and that we may need some additional testing done in the middle between these two testing stages. And so Mark went ahead and developed another test, which I now want to look at. And this test is called nested call. And everything that you see here was designed by Mark. So you see that we have a set of files, a single VM file, sysvm, and then a set of corresponding test files, as well as 2 HTML files. Now, this test once again, it closes some gaps between simple function and Fibonacci element in terms of the different things that Mark decided to test. And we recommend that you do this test in case simple function passes and Fibonacci element fails. If that is the case, you may want to go back and use nested call in order to localize the problems in your VM translator better. And finally, this test is very well documented using the 2 HTML files here that Mark has written. So we just suggest that you, if needed, read those files and follow Mark's guidelines. All right, so that's what I wanted to say about function calling. And the last test that we have to run is called statics test. And that's what we see here. Once again, it consists of several VM files, and therefore, once again, we have to apply your VM translator to the entire directory, and the result, once again, will be a single file written in a Hack assembly language. And let's see, what is the problem to which this thing is the solution? Well, first of all, here is class1.vm, and we see that this program stores 2 pushes, and then before returning, it pushes 0 onto this. Don't worry. Then there's one more function in this file, returns as is straightforward. You will realize most. I mean, they have exactly the same logic, except for some maybe. Even though this is a file, we introduce just slightly. So how do we do it? Well, as I handle the files that we just saw abbreviated, we in it, and then Coan will populate its static segment with 6 and 8. That's it. We enter this infinite loop, or expect to see on the state in arithmetic. All right, here is designed to correctly test additional tests in the context of this. Well, first of all, you will need all the test program in the chapter that we used also in Project 7. So I'm not going to a description of Project 8. I wish So, welcome to the last unit of Module 2 called Perspective. And to remind you, we are using these perspective units to provide some historical context and gossip a little bit about the industry and explain why the stuff that we do in Nando Tetris is extremely applicable and practical outside the context of this course. So we're doing this using questions that we normally get when we teach this course. And the first question is, how useful is this VM language? Does it really make the writing of compilers easy? Well, the VM language is surprisingly powerful. And in order to appreciate it, you can take a second look at some of the Jack applications that we showed during this module and compare the Jack code of these applications with the VM code which was generated by the Jack compiler when it translated these Jack programs into the VM language. If you will do so, and if you will do some line counting, you will realize that each line of high-level Jack code generates an average of about 4 lines of compiled VM code, which is quite remarkable. So even without knowing much about compilation, because we haven't discussed compilation yet, you should be impressed, I think, by the compactness and readability of the VM code which is generated by the Jack compiler. So the question arises, which is, how does this compiler get away with generating so little code? Well, the answer is that this is a 2-tier compiler, and therefore the compiler can happily assume that there is another agent, a VM implementation, that handles all the translation tasks from the VM level all the way down to machine language. And that's exactly the VM translator that we've built in the last 2 modules. In fact, if you take a big picture approach, we've just finished developing the second back-end part of the overall compilation model. So the good news is that when we'll get to write the rest of the compiler in modules 4 and 5, we will have far less work to do compared to, say, writing a C++ compiler, which forces you to translate everything all the way from C++ down to machine language without an intermediate level. And therefore, the hard work. So the good news is that when we'll get to write the rest of the compiler in modules 4 and 5, we will have far less work to do compared to, say, writing a C++ compiler, which forces you to translate everything all the way from C++ down to machine language without an intermediate level. And therefore, the hard work that you did in the last 2 modules will pay off big time later in the course when you will get to develop the front-end part of the compilation model, which we call simply compiler. And that's the part that generates the VM code that we discussed and implemented in this module and the previous one. So, to wrap up, the virtual machine is an extremely powerful and practical idea, which is a very important piece of the Java architecture, the C# architecture. And in fact, today Microsoft also has a 2-tier compiler for C++. So if you want, you can also translate C++ programs into an intermediate VM layer. But if you do so, you're going to lose a lot of efficiency, which is the hallmark of using C++ at the first place. So let's see what is the next question. Well, in fact, it's directly relevant to what I just discussed. What about efficiency? Why is C++ more efficient than Java? Well, obviously, any 2-stage translation model entails additional overhead and results in more lines of less efficient machine code. If you're not convinced, try translating something from English to French by first translating from English to Spanish and then from Spanish to French. Obviously, the second technique will be more cumbersome and it will yield more cumbersome results. So, which is more desirable? A 2-tier Java program that eventually generates 1,000 lines of machine code, or an equivalent C++ program that does the same thing with 300 lines of machine code, that run 3 times faster? Which is more desirable? Well, the pragmatic answer is that today's computers are amazingly swift. And therefore, in many important applications, a drop of 300% in efficiency is not really noticeable. And of course, there are many areas like real-time signal processing and embedded systems in which every efficiency gain is cherished and important. And for these applications, languages like C and C++ are indispensable and much more applicable than Java. But in numerous other domains, the elegance and security provided by languages like Java and C# and Python more than compensate for the loss in efficiency, which, once again, is hardly noticeable in numerous applications out there. So moving along, let's see what is the third question. Security. Why is Java more secure than C++? And what does this have to do with our VM architecture? Well, you may know that VM code is sometimes referred to as managed code. And I think that this term was first introduced by Microsoft. Once again, as you may know, the centerpiece of the .NET framework is a virtual machine called CLR. It stands for Common Language Runtime. This is the equivalent of Java's JVM. So C# compilers generate VM code is a virtual machine called CLR. It stands for Common Language Runtime. This is the equivalent. And I think that this term was first introduced by Microsoft. Once again, as you may know, the centerpiece of the .NET framework is a virtual machine called CLR. It stands for Common Language Runtime. This is the equivalent of Java's JVM. So C# compilers generate VM code, which in the world of Microsoft is known as IL, intermediate language. And this IL code, similar to bytecode, is designed to be handled further by some CLR implementation. So to distinguish between code that is handled by the CLR, like C#, and code that runs directly on the target hardware platform, like C++, Microsoft calls the former managed code and the latter unmanaged code. And so this notion of managed, which really stuck not only in Microsoft, but by anyone who uses the VM artifact, this notion of managed comes from the observation that this notion of managed, which really stuck not only in Microsoft, but by anyone who uses the VM artifact, this notion of managed comes from the observation that when the code runs on some virtual machine environment, like the CLR or the JVM or our own VM translator, we can do all sorts of useful things with this code, in addition for just executing it blindly. For example, we can inspect the VM code and look for security breaches. it's much easier to analyze the semantics of VM programs compared to machine language programs, which are far more elaborate and cryptic. Also, let's not forget that the VM code must be handled by some virtual machine implementation. So we can design this implementation in a way that creates what is sometimes called a sandbox effect. The idea is that during runtime, executing programs can never reach out of the sandbox and mess up with toys that they are not allowed to manipulate, like the host RAM. And that's extremely important in a world in which software is routinely downloaded off the internet to your computer or to your cell phone without even you knowing this. And this software comes from all sorts of unknown sources. So in that respect, the VM implementation that runs on your PC or on your cell phone can be viewed not only as an enabling technology, but also as a security layer that protects your device from malicious code. And that's another very important advantage of the VM model. All right, I wish to end this module with a general observation about the virtue of separating abstraction from implementation on sources. So in that respect, the VM implementation that runs on your PC or on your cell phone can be viewed not only as an enabling technology, but also as a security layer that protects your device from malicious code. And that's another very important advantage of the VM model. All right, I wish to end this module with a general observation about the virtue of separating abstraction from implementation, which is something that we emphasize in almost every unit and module in our NAND to Tetris courses. Recall that VM functions access their memory segments using commands like push argument 2, pop local 1, push static 7, and so on. Now, in doing so, VM functions have no idea whatsoever how these values are actually represented on the host RAM, or how they are saved and reinstated during the function call and return protocol. In other words, the VM code treats memory segments as abstractions without worrying at all how this abstraction is actually realized by the VM implementation. Now, this complete separation of abstraction and implementation implies that it implies many important things, but one of them is that developers of compilers that generate VM code don't have to bother at all about how this VM code will end up running, and they don't have to bother at all about the host platform. The host platform for them is a virtual machine. And that's very important because compiler developers have enough problems of their own to worry about, as you will soon realize in the next 3 modules when you will develop our own compiler. But cheer up, you've just completed developing the first half of a compiler for a high-level, object-based programming language. That's incredible. This is a tremendous achievement, and you should feel very proud of yourself. And with this feeling of pride, we are wrapping up Module 2, and I will see you again in Module 3, in which we present our high-level language.